Happy Friday, everyone. TGIF. It's May 1st. We're excited. It's a new month. Hopefully it'll bring a lot of really good things, especially here at PALS TV. So welcome back to our final episode of the week. We've had a lot of fun all throughout the week, bringing you a wide variety of content and a lot of different topics. So I know we've had a blast doing this, and I hope you've enjoyed it as well. It's been a tremendous success to be able to continue to have our contact with all of you and maintain our relationships. It's been very important to all of us that we're continuing to see you and talk to you as much as possible and being able to just communicate. That's been very important to us, and I hope you've enjoyed it as well. So we'll be taking the weekend off, and we'll come back on Monday after our segment today and our episodes. And we have an amazing lineup again for you come next week. So really looking forward to that. A lot of exciting topics again, and it should be a lot of fun. So we've been having fun with this. I want you to have fun with this. So we're gonna try out different things on Monday. I'd like to show our love for PALS and celebrate PALS. So whatever PALS clothes, shirts, hats, whatever it is you have with the logo on it, wear it. Get on Zoom and show your pride in what we do and show us that you miss us as well, because we definitely miss you. So today we're going to be wrapping up in Steubenville with our tour of the Smithsonian. It's been fantastic. I personally have really enjoyed Amanda's tour and the detail she's gone into with a lot of the different exhibits. It's been wonderful. And really looking forward to our last day in the Smithsonian and then what's to come in the future. So live from Steubenville, we have Amanda.
Hi, everyone. So today, like Aaron said, today is our last day at the Smithsonian, and we are checking out the Hall of the Gemstones. So we've got all kinds of different gemstones and some interesting things. And then next week, we are going to be heading to the National Air Force Museum. So that will be for next week, and I look forward to seeing everyone then. So let's go ahead and I'll share my screen with you guys. Wait a minute. Helps if I click the right button here. Move that over here. This over here. Okay, now we are ready. Okay, now I can share my screen with you guys. Share. And I will get this up to full screen. So this is where we are going to be, this area right here today. And that will make up our tour of the Smithsonian. I know we didn't hit the ground floor, but if you can, I'll show you in here. There's really nothing in the ground floor for us to explore. You got, a couple cafeterias and gift shops. And I don't know about you, but if I can't buy anything at the gift shop, I don't want to look at it. So off to the second floor we go. Now, we looked at the Hope Diamond yesterday. So this is the main beginning of it, and this is the National Gem Collection. More than 7,500 individual gemstones ranging from less than half a carat to almost 23,000 carats fill the cases in this gallery. Like all precious gems, each was cut from a mineral crystal that grew naturally within the earth. The National Gem Collection totals more than 10,000 specimens and is considered one of the world's finest. Virtually all of the pieces are gifts from individuals. The gems now belong to the people of the United States. All right, so our first gem right off the bat is the Don Pedro Aquamarine, and it is 10,363 carats, and it was found in Brazil. An immense beryl crystal found in the late 1980s yielded the Dom Pedro, the largest known aquamarine gem. The original crystal was almost 2 feet in length and weighed nearly 60 pounds. In 1992-93, gem artist Bernard fashioned the gem and named it after the first two emperors of Brazil, a pattern of tapering negative cuts and faceted into two reverse faces of the obelisk. These facets reflect the light, making it appear to glow from within. The vertical lines near the base are hollow tubes that form naturally in the original crystal. And zoom in a little bit and you can see the crystal. Right here, the tubes that are talking about inside that have formed naturally. It's pretty interesting how nature did that without any help from us. So as we spin around to over here, mineral, crystal, or gem, what is the difference? Each of the topaz specimens in this case is a mineral, a solid inorganic chemical compound that forms naturally. Most minerals are crystals. A crystal is solid with an orderly repeating internal pattern of atoms. Mineral crystals that grow under ideal conditions have geometric shapes with smooth faces like the two exceptional examples on your left. So that's these right here. A gem is a mineral crystal that has been cut and polished, like the enormous ones to your right. So these are both examples of topaz, but one is considered a mineral because it hasn't been cut and made into anything real pretty. Over here, we consider this a gem because they've been polished and they've been cut to, you know, this one looks like a diamond, this one kind of looks like a disco ball. Okay, crystal to gem. How does a crystal become a gem? Skilled gem cutters transform mineral crystals into sparkling gems. The exact procedure varies with the type of mineral desired to cut. Below, a series of 4 photographs show how one aquamarine crystal was cut into gems. So there was the original, and then they cut it into half, and they polished it, and they cut it down some more, and they buffed it, and then they got the finished piece. So let's head over to our next section of the museum. There's some more of our topaz. And then if we zoom in over here, we have some beautiful jewelry that are made of rubies and sapphires. This is a sapphire and diamond necklace. This is a Bismarck sapphire necklace. It's a very, very pretty jewelry that was probably worn by royalty at some point. Rubies and sapphires, prized for their beautiful colors, rubies and sapphires are both gem varieties of the mineral corundum, the second hardest mineral after the diamond. Colorless in its pure state, corundum rarely has sufficient clarity or richness of color to be a gemstone. When it does, the difference between a ruby and a sapphire is just a tiny bit of impurity. Rubies are by definition red. The color results from the light interacting with a few atoms of coronium trapped at as the crystals grew. Ruby is also the July birthstone. Sapphires are corundum crystals in all colors but red. Best known are the blue varieties, tinted by iron and titanium impurities. Sapphire is the September birthstone. So does anyone here have a birthday in July or September? No, nobody on here for July or September? All right. So our next gem, we have stars and cat eyes. Magically from the depths of mineral crystals, stars shine and cat eyes gleam. Tiny needle-shaped crystals that grew within larger crystals cause these optical effects. Light reflects off the needles, which are commonly crystals of the mineral rutile. Depending on whether the needles grew in 3 dimensions or 1, the result is a star or cat eye. To highlight the effect, a gem must be cut as a kubakon and in the correct orientation. So you can see a little bit, we can't get real close. I'm as close as I can zoom in here, but you can see how it kind of looks like there's a star at the end of the things. Okay, so we have some more gems here. Unfortunately, I cannot see them. Let's take a spin here. We'll see some closer up at that. And there's our topaz we saw earlier. So let's bounce over here. And over here we have all these different minerals. So many colors. This stunning array gives you a glimpse of Earth's incredible palette of mineral colors. Some minerals always come in the same color. For example, malachite is always green, rhodochrosite a shade of pink or red. Others, such as quartz, are normally colorless, but boast a rainbow of hues if they contain impurities, inclusions, or defects in their atomic structures. Look and discover common coloring agents such as iron, copper, and manganese in the chemical formulas. A rhodochrosite slab cut from a cluster of stalactites, lapis lazuli, an ornamental stone composed mainly of the blue mineral lazurite. So let's zoom in here. We got, so up on top we have an etherite, a fluorite, evite, sodalite. It's got that very pretty blue coloring. Azurine, blue. So we have some purple quartz here. And we have a voxite and lazulite, some more azurite. So it just depends on what minerals or impurities the stone has that determines its colors. So I'll zoom out and we can just see all of the different stones in this section here. This is very pretty up here. Let's see what that is. Rhodoconite. It's very pretty. Okay, so as we come over here, doop, doop, doop. Here's some more. This is pyrite right here. The first thing you notice about these pyrite specimens is their golden luster, but look more closely to the striking diversity of crystal shapes. These pyrite crystals are all built of iron and sulfur atoms, linked in the same cubic pattern, but different growth conditions create distinctive external shapes. Cubes tend to grow under low temperatures from solutions with low concentrations of iron and sulfur. Octahedrons and pyrithydrons result from higher temperatures and more concentrated solution. So you can see, there it is. Does anyone know? Now keep in mind it's gold. Does anybody know, raise your hand and I'll get to you, what another name for pyrite is? Okay, give me 1 minute. I see you, Sean. What you got for me, Sean? What is it?
Gold.
Fool's gold. That is correct. It looks like gold, but it is not. Good job. All right, so that was that section. Let's do a spin. All of these mineral crystals grew naturally within the earth. The keys to their varied forms, whether they are cubes, needles, blades, or a myriad of other shapes, lie inside them. Different kinds of atoms arrange themselves in particular patterns, determining each crystal's basic shape. As crystals grow, differences in temperature and chemical composition cause fascinating variations. So you can see here, you got that one. Those are pretty nifty stones here. We got barite, got some beryl, solasite. So different temperatures determine what, and different pressure determines what they're going to look like. Let's head over here. So this, we have different, this right here is asbestos. Are those shaggy looking minerals collectively called asbestos hazardous to your health? Some are under certain circumstances. Asbestos is a commercial term for several distinctive fibrous minerals. Because each mineral has a unique atomic structure, chemistry, and a set of properties, evaluating the health risks associated with asbestos is a complex problem. Despite their controversy about their safety, some asbestos minerals are still used because of their strength and resistance to heat. So here's some asbestos here. It's called riebeckite, a form of asbestos. Crystotile. So you can see the long fibers that make up asbestos. Can anybody tell me what asbestos used to be put into something that we used to build houses, particularly something that keeps your houses warm? What was asbestos used to be in? It's not in it anymore, though. Does anyone have an idea? Asbestos used to be in our insulation that they would put into walls to keep heat in the house. So over here, we just have some more stones. These are out of the Earth's crust, which is the ground. There we go, just a quick look at all those there. It's amazing how many different types of minerals and stones there are. Over here, we got some more. We got some halides, some sulfates, and some phosphorus stones. Let's zoom in a little bit, see what we can see. Okay, and I think that's all we got in this little hallway here. Let's head over to 4. Oh, I see some more of these purple ones. So these are quartz right here. And these are some really large crystals. So these are crystals here. We have quartz crystals. There's all the different colors. You spin around. We have some more sulfides and oxides. So these are going to be stones that are more metallic in color. See how it almost looks like metal? Oxides are minerals that combine oxygen with one or more elements, usually metal. One of the most familiar oxide minerals is ice, H2O. 2 of the many economically important oxides are hematite and magnetite, both iron ores. So that's why they have the silver colors. Okay, let's go to gems and minerals 5. Here we have some more big stones. Just telling us a little bit more. Let's see what this big purple guy is. He's kind of neat looking. Looks like it says it's fluorite. See if we see anything. How do crystals grow? In many wonderful and mysterious ways, crystals start to grow when groups of atoms lock together in a regular repeating pattern. As they grow, the solution from which they are growing can change composition. More atoms can be supplied to one side than to others. Crystals can stop growing, begin to dissolve, and then just start growing again. Just spin around here. See if we can figure out what this is here. What are pegmatites? I'm sorry, that's these here. And why are they so important? Pegmatites are exceptionally cone-grained rocks born of modern rock or magma beneath the Earth's surface. They produce many of the crystal glass giants of the mineral kingdom. So that's where a lot of these big guys come from. We can zoom in a little bit. You can see some more pegmites there. They're the big crystals. And here we have a geode. So geodes, as you can see from the outside, it just looks like a regular rock. And then when you crack it open inside, you'll see all these minerals and different things inside. We have some more examples of geodes here. All right, I've gotten lost in the museum again. So this is gems and mining here. So what do you guys think this is? Caitlin, what do you think it is?
I think it's gold.
You are right, it is gold. So let's find out a little bit about it. Gold, in this case, all that glitters is gold, beautiful and durable, a symbol of wealth and power. Gold has been one of the most desired metals. More than 5,000 years ago, Egyptians transformed gold into objects of royal splendor. More recently, the quest for gold accelerated the settlement of Australia, Alaska, and the American West. Native gold comes in many spectacular shapes, crystals, ribbons, wires, and nuggets. Look and discover a large nugget that weighs 2.55 kilograms or 5.6 pounds. Gold together with quartz, a common association, and a specimen that shows real gold sitting on fool's gold, pyrite. So let's see here, see what we can find. So there is all the gold, and that's what it looks like in its natural state. You know, we're used to seeing gold in jewelry or gold bars and things of that sort, but typically it just looks like a shiny rock until it's all polished up and melted down and turned into our gold bars and our jewelry. So if you notice over here, this is a lot of gold. This has all come from California. Eureka, in 1848, the discovery of gold touched off the great California, what? It was called the California, what? Anyone know what it was? It was the California Gold Rush. Nearly 100 years later, these pieces were found in California's Mother Lode. The impressive triple ribbon weighs 455 grams, 1 pound, the English unit of weight for precious metals. Okay, and there's all the gold, well, not all the gold, but some of the gold that they found in California. Why is gold so valuable? Gold is scarce. Throughout all of history, only about 116,000 metric tons have been found, enough to make a cube about 18 meters or 59 feet on a side. Gold is beautiful. Ancient cultures equated its brilliance with the sun's, and we still prize its glow in jewelry and ornaments. And gold has properties valuable to industry, such as excellent electrical conductivity and corrosion resistance. And why does it stay so shiny? Gold doesn't tarnish. That is, it does not chemically react to other elements such as oxygen and sulfur. No matter how long gold nuggets tumble in a stream, they always keep their gleam. So gold can't tarnish. Let's see what we got over here. Mineral or ore. A mineral is a solid inorganic compound made from one or more elements that form naturally. Metal is an element with particular properties such as malleability and the ability to conduct heat and electricity. We extract metals from minerals. An ore is a mineral or rock that can be mined or processed for profit. A mineral may be an ore in one place but not in another. For example, The honey-colored area of this rock is the mineral sphalerite. As its chemical formula indicates, it contains the metal zinc. Sulfur contains enough zinc, 67% by weight, and is plentiful enough in this area of Tennessee to make it economical to mine. So here it is in ore. So if you look, you can see the different coloring. That's ore down in there. So that would be zinc. Pay dirt. Most metals we value are dispersed in the rocks of the Earth's crust. Miners look for places where natural processes have concentrated metals into mineral deposits that can be mixed economically. Most of the specimens you see in this exhibit were recovered during during mining. See for yourself. Peek through the opening to your left to view a, oh, well, we can't peek over there, unfortunately. All right, so let's head over here. Let's go to mining 3. These are some more things that have been mined. Man, that is a big guy right there. Let's see if we can see. That is calcite right here. Saved from the crusher. Among collectors, Mississippi Valley type deposits are renowned for their impressive mineral specimens. This case highlights specimens from several well-known deposits in the U.S. Some of the minerals, such as galena, are ores. Others, such as calcite, are not. A few, such as fluorite, are ores in some mines, but not in others. Spectacular mineral specimens like these are rare. Most are destroyed as a result of mining. So these are some that they saved. The tri-state district of Missouri, Oklahoma, and Kansas was a prime source of lead and zinc from 1848 to 1964. Galena, above and below, is an ore of lead. Mineral specimens from tri-state are world-renowned. Well, there's some of our mineral specimens. So let's see where I gotta go. I'm lost in the museum again. Okay, and these are some more ores. Stainless steel pans contain nickel, as do some coins. Nickel and cobalt are used to make magnets and specialty alloys for jet engine. Cobalt toughens cutting tools and is used as an industrial catalyst and pigment in blue glass. So let's see if we can find some nickel. Nickel, nickel, nickel. Nickel, nickel. Nickel! We found it. There's some of the nickel right there. A lot of people, this is something for me, I'm allergic to nickel, so I really have to pay attention to what kind of jewelry I wear, because if it has nickel in it, it'll cause me to break out. A lot of people actually are allergic to that, and that's because it's a mineral. Okay, there's just an example of a rock formation here. These are rock columns. So you can see that's all the different rocks pushed together, almost like a puzzle, but broken apart. We spin over here. Natural sculptures. Water, wind, and ice shape these day after day, year after year, century after century. These 3 agents of change: polish, scratch, gouge, and carve even the hardest rocks. So just an example right there. You can see the different scratches and scrapes. You know, it's telling us it's a smoother stone from wind and sand pushing up against it. We have some different rocks over here. This looks like it's granite right here. Oops. Look, enjoy, preserve. We have a stalagmite here and a stalactite. So peer into a subterranean wonderland. How many different kinds of cave formations can you spot? The ones displayed here come from a number of limestone caves and are assembled to look like a grotto from Luray Caverns in Virginia's Shenandoah Valley. Stalactite and icicle-shaped formations that grew down from the cave roof early in their growth. Stalactites resemble soda straws. So right here, this is a stalactite. A good way to remember it is stalactite, it hangs tight to the ceiling. Then we also have a stalagmite, a pillar-shaped formation that grew up from a cave floor. The drip and flow of water, along with the varying rate of growth, produce the specimen's texture. You can see right there, there's a stalagmite. So over here, we have some clay concretions. So these are things that naturally formed in nature that they pulled out of clay. You have quartz, sectarian, you know, excuse me, nature can naturally produce concrete. It's not just a man-made thing. More than a dash of salt. The colorful layers in this rock are made entirely of 2 salt minerals. This evaporate formed 250 million years ago when briny water evaporated from an ancient inland sea. Left behind were the sodium, potassium, and chlorine in the water. They combined to form a bluish-white halite and orange silverite. So there's some salt. If all the seawater in this 10-liter bottle evaporated, it would yield these amounts of minerals. Seawater typically contains 3.5% by weight of dissolved minerals. So you can see, if it would dissolve, that would be all the minerals that would come out of it. We have, let's see here, calcite, sylvite, gypsum, magnesium, and halite. So you can see there's quite a bit of halite in there. We have 1, 2, 3 plates of halite. Okay. Okay, we've got some more stuff here. Rocks transform. Inside their chrysalises, caterpillars change into butterflies. This is called metamorphosis, from a Latin word that means to transform. Inside Earth, heat and pressure change a rock's minerals from one side to another. This too is called metamorphism. In each case, the basic ingredients stay the same. They're just assembled into a new form. These 3 specimens show how the volcanic rock basalt can change both its minerals and its appearance as it is buried deeper and deeper in the Earth's crust. So this is the real deep. So deeper is get down. Keep look too as they, excuse me. So this would be closest up to the top. And then as they go deeper, it gets hotter, and you can see a difference from this one up here to this one down here. It's smoother, it's flatter, the color is a lot more different than what you have up here. Okay, let's take a spin around here, see if there's anything else in this section. Does not appear to really be anything. Right here, it talks a little bit of magma and a lava lake. Does anybody know what magma is made out of? Caitlin, what's magma made out of?
Lava.
Well, lava is magma, yes, but lava or magma is made out of rock, melted rock. During a 36-day eruption in 1959, the Hawaii volcano Kilauea produced rivers of red-hot lava that filled the adjacent crater to a depth of 135 meters and created a lake of molten rock. The lava lake provided scientists with a natural laboratory and a rare opportunity, a chance to observe lava slowly crystallizing. From 1959 through the early 1990s, they closely monitored the lake as it cooled and solidified. Okay, that was pretty neat. Over here we have some rocks that were formed from glaciers moving. All of these rocks started out as fluid magma, yet their final forms vary widely. As indigenous rocks solidify below and at the Earth's surface, they are shaped by different physical and chemical conditions. The unusual features of these volcanic and plutonic rocks reflect a variety of indigenous processes. Look for a rock that formed when magma was injected into another rock. It fell into a cooling body of magma or magma froth while erupting. So this one here, it looks like the magma had dripped into something cooler, how it looks like little raindrops. Here we have some granite. Pretty nifty. Go to our next stop. Continents. Continents adrift throughout history. People assume that continents were fixed in place. In 1912, German meteorologist Alfred challenged this prevailing notion. He argued that today's continents were once part of a supercontinent called Pangaea. We learned about that when we looked at the dinosaur bones. From the Greek words meaning all earth. About 200 million years ago, it broke into pieces that drifted apart and eventually became known as today's continents. This idea became known as the theory of continental drift. So that's what it might have looked like 200 million years ago. And that's the view today, how it slid apart. You see how it almost looks like this part right here could slide over into this part just like a puzzle. Spreading ridges. Just shows how when things collide and push up against each other, they push rock up and make different rock formations. So right here, I believe this is a piece from the Mid-Atlantic Ridge, one of Earth's longest mountain ranges. The Mid-Atlantic bisects the Atlantic Ocean for 11,300 kilometers, but hidden from our view, except where it straddles a hot lava lake. The combined volcanic activity of the ridge and one hot lava lake have produced the world's largest volcanic island, Iceland. Like splitting a seam, magma wells up at the ridge crest, adds to the spreading plates on either side, ever so slowly widening the Atlantic Ocean. So as that pushes up through, it creates islands. As also as plates in the earth push together, that's also what can create mountains. So let's head on over here. Oh my goodness, that's a big earth. Over here, they're talking about the fault lines. So fault lines are cracks in the Earth's crust. And what happens is when we have an earthquake or something like that, it's because those fault lines are pushing up against each other and shaking. And that's what, and really providing a lot of pressure. And that's what creates earthquakes. Clues from rocks. It's no coincidence that most of these rocks are olive green. Some of their colors come from olivine, the most abundant mineral in Earth's upper mantle. That's where all these rocks called peridites come from. Besides telling us what the upper mantle is made of, peridites record geological processes that take place in this inaccessible layer of Earth. So it's a section of Earth we can't get to, so it kind of tells us what is under there. And the different pressure. Oops, I've already been there. Oh no. I'm lost. Lost in the museum. Okay. Down here we have Henbury. This specimen fell about 10,000 years ago in a shower of meteorites that left a cluster of 13 craters. Incendiary passage through the atmosphere produced a cone-like shape and small depression. So these right here are all meteorites that have hit the Earth at some point and fallen into our atmosphere. They don't look very big, but I bet when they fell, they created a lot of damage wherever they fell. Let's see what else is over here. Nope, we already saw that. And this is our last section here. We have Antarctica, and that's where the majority of meteorites fall. So there are a few more meteorites. These ones are smaller. Some long lost cousins. And that is going to do it for our gems. We've made it through and we are finished visiting the Smithsonian. So next week, like I told you guys, we're going to be exploring the Air Force Museum, and I hope to see everybody then. Thanks very much, guys.
Thank you, Amanda. Another wonderful tour of the Smithsonian. Does anyone have any questions for Amanda before we finish up this segment? Anything you personally enjoyed about the Smithsonian? You might maybe want to learn a little bit more about, and we can try to get you some of that information. Okay. Well, please send anything over to us that you might have a suggestion that we can kind of incorporate into our PALS TV segments. These have been a lot of fun. We need to get those recreational activities and some of the outings in our life, but this is a unique way of us trying to bring that to you for right now until we can all be together again. So can't thank Amanda enough for her wonderful tour this week of the Smithsonian. Learned so much, and I think, you know, it's very valuable that we really can connect with you this way. So thank you for being a part of it, and we will see you in about 15 minutes as we go live from Gallia County next. So really enjoyed our time in Steubenville this week, though. So thank you, Amanda, and see everyone here at the top of the hour around 11 o'clock.
Bye, everyone.